a little bit of context about the talk. So I did a bunch of different kinds of projects in the broad area of AI safety. My initial work was on different topics around RLHF, which is basically how to make language models do what we would like them to do. Then at Anthropic, I was doing similar stuff at scale, building fine-tuning pipelines for production models. And right now I am at the UK RSF Institute. That's a government agency focused on evaluating frontier models on dangerous capabilities, trying to investigate risks associated with them, and trying to inform policymakers and the national security community about those risks. Specifically, the thing I work on is safety cases for AI. That basically means trying to figure out what kind of evidence would we need to provide to convince ourselves that a given future superhuman model would be safe to be deployed. But my talk is mostly going to be about stuff I did in this first part on the slide. This is mostly because I cannot really comment about Anthropic, and at AC we are only starting to publish our thinking. And also, I, as a civil servant, am not allowed to have spicy takes, but I am happy to answer questions. Coming back to the next slide. Language models are pre-trained to imitate internet text. We know that internet text contains a lot of undesirable content, like falsehoods, offensive comments, bad quality code. So, and this is just imitating that is clearly not what we would like AI assistants like ChatGPT or Claude to do. And this motivates this general problem that we sometimes call the alignment problem. How to bridge this gap between the pre-training distribution and a helpful and harmless assistant. And the go-to solution to that is reinforcement learning from human feedback, or RLHF, which basically means fine-tuning a model trained to imitate internet text to maximize some reward function representing human preferences. And it seems that RLHF works remarkably well at scale if you look at ChatGPT or Claude. But you could ask whether really just unconstrained reward maximization is the right perspective to describe what's happening when we do RLHF on production models, and whether it should be seen as the ultimate solution to AI safety. And in this talk, I would like to offer an alternative perspective of framing alignment as conditioning on subsequent pieces of information about human preferences. So here's the idea. A language model is a probability distribution over tokens. And we would like to condition this distribution on this new variable representing human preferences. And I kind of like to see it as Bayesian inference, updating a base model on some evidence about human preferences provided by human feedback. And you could then see this posterior distribution as the target we are aiming at, the aligned language model. And a fun thing is that RLHF can itself be seen as conditioning a base model on evidence. I will show in a few slides that the objective of RLHF is actually equivalent to minimizing KL from a certain target distribution. But this whole framework is much richer than that. I will then go on to consider more expressive posteriors that could involve latent variables or some calls to tools that implicitly define some distribution. And finally, in the last piece of the talk, I will consider the case in which you could learn the conditional distribution directly by pre-training a model with some pieces of feedback given at pre-training time. But before I do that, let me start with convincing you to this underexplored perspective of what's happening during RLHF fine-tuning. So in RLHF, we start with this base model. We have a reward function. And typically, we maximize this objective, which is expected reward, minus some KL penalty that ensures that we tend to stay close to the base model, that we are not just maximizing rewards, maximizing the reward function without any constraints. And the fun thing is that this formulation is actually equivalent to another KL. So this whole objective, maximizing this whole objective is equivalent to minimizing another KL between your policy and some target distribution. The proof of this fact is simple, but I am not going through that. The important thing, I guess, is that the target distribution implicit in the RLHF objective is a Bayesian posterior, and this particular objective in RLHF corresponds to variational inference, an established approach in Bayesian inference. So in some sense, you could say that RLHF is secretly doing conditioning. And then I will try to convince you that this perspective is actually somewhat insightful. So one thing that makes it insightful is that if you have your policy and some target distribution, there is many ways of moving them closer together. The thing that is actually being used in RLHF, in RL with KL penalties, is what's called the reverse KL. But some of you might know that KL is not symmetric. The order of argument matters. You could also try to minimize forward KL, and that gives rise to a different algorithm that has somewhat different properties. Mathematically, maximizing forward KL is no longer equivalent to reinforcement learning. And you could consider some other distributions, like the Jensen-Shannon, which is kind of something in between reverse and forward KL, or the total variation distance. We tried to build a general framework comparing those different objectives. So you could say that the whole thing can be seen as minimizing an f-divergence. F-divergences are this general family of different measures of dissimilarity between probability distributions. And then you can ask which objective is the best one to optimize and what inductive biases they present. So we try to do a quick study. I will skip the details here and just move to the bottom line. If you just focus on one aspect, the trade-off between alignment and diversity of different objectives, by alignment, I kind of just mean the amount of reward that you can get via optimizing a particular objective. So, for example, how good you are at making the model more helpful as you maximize a given objective, versus diversity. Here it's measured in terms of entropy, but you can have other measures. It seems that reverse KL, the thing that you use in traditional RLHF, is particularly good for maximizing alignment, frequently at the cost of some mode collapse of your model. Forward KL is much better for preserving entropy of original model, which is sometimes useful in use cases where you care a lot about diversity of your samples. And you can also have some objectives in between. So Jensen-Shannon is the symmetrized version of forward and reverse KL. Unsurprisingly, it is kind of between them on the spectrum, and it consistently appears on the Pareto frontier. So far I talked about objectives that you use to minimize. So objectives that are some measures of dissimilarity between your policy and the target distribution that you like to approach. Then, in the second part, I will focus on the complementary problem, the problem of designing the target distribution that you would like to approximate. And this is based on work by Jeremy Scheuer and Angelica Chen that I contributed to. So in traditional RLHF, language models learn from scalar feedback. They do an action, they get some reward, and that reward is a scalar number. This is not how we teach kids in school. In school, we typically give students feedback expressed in natural language. And you could say that language models should be good with language. And also, like, just thinking from first principles, it seems that natural language should be a much richer form of feedback than just a single scalar number. It's much more informationally dense. It comes with useful abstractions that has evolved to match human ontology, to match how humans use tools. And you could also argue that just expressing feedback in language makes giving process-based supervision much easier. For example, in many cases, you might want to supervise individual steps of a language model that lead to an outcome. For example, when the language model tries to figure out a math proof. Whereas in standard RLHF, you would just reward the final outcome, but not steps leading to it. And you could see language feedback as a particular latent variable in the target posterior that you would like to approximate. The way I like to see it is that a prior language model conditioned on human preferences contains some implicit latent variable. An initial output, x prime, a language feedback that a human would provide on that output, and then the target distribution can be factored into several distributions corresponding to an initial language model, human providing feedback, and the language model conditioned on that feedback. So let's consider an example to see how this chain unrolls. First, you have an initial language model generating a first output. It could be a summary of a document. Then we show it to a human. A human provides feedback expressed in natural language. Then we condition the language model on both the initial output and the human provided feedback, and we ask the language model to generate a refinement. For example, a new summary that fixes the flaws in the first summary that have been pointed out by the human. And then we generate a few of those refinements, and then we select the best one using perseverance sampling against a reward model. And then, of course, it's not convenient to have a human in the loop at deployment time. So what you do in practice, you could just fine-tune the language model on its best refinements, effectively distilling this whole target distribution implicitly defined in terms of human feedback to a single parametric model that you can sample from a normal model. And we call the iterative procedure for doing that imitation from language feedback. It kind of can be seen as an EM algorithm for training latent variable models, where in the E step, you are constructing a proposal distribution using the current language model, and in the N step, you are fine-tuning the current language model on those generated refinements. We evaluated ILF on summarization and code generation tasks, but for now, let me just focus on summarization. So first, to evaluate the E step, we generated summaries from a given language model. We gathered human feedback on them, and we compared 4 methods for generating refined summaries. We then asked humans whether they prefer the refined summaries over initial summaries. So just generating a refined summary zero shot helps a bit. So here we are just showing the model an initial summary, and we asked for a second one. And just this tends to be a bit better. So it is a baseline. Then you could generate a refinement based on feedback provided by a human, and that helps a bit more. You could argue that kind of significantly more. And then if you add best of n sampling on top of that, it works even better. And that's the red bar is our main method here, which obtains a win rate of 70%. So that means that in 70% of the cases, the refined summaries will be preferred over an initial summary by a human. But then you could also compare that with just asking a human to write from scratch a new code summaries. And these are preferred much more often. So in this sense, the whole procedure still leads to subhuman summarization performance. And then in the second part, we evaluated the whole single EM cycle of ILF by generating from fine-tuned models and measuring win rates against human summaries from a previous model. So here we fine-tune models on those refined summaries, effectively distilling this chain, and see how this scale with the number of documents in the training set of that model. And here ILF, that's the red line, outperforms simple fine-tuning on cold human summaries, and that's the blue line. So here, compare again the red bar and the blue bar. Here, instead of just evaluating those samples, asking humans which one they prefer, we use those samples as fine-tuning data. We fine-tune models on them, and we evaluate samples from those models. So here, clearly, the blue bar is better than the red bar. But here, the red one is actually better than the blue one. And that is very surprising. It means that fine-tuning on better data leads to worse results than fine-tuning on worse data. And yeah, that is surprising. It suggests that maybe just language model generated data are more tailored to a particular model. So the model is able to learn from them more sample efficiently. That could be one explanation. We don't really know. As a skyline, you could compare ILF to best of 64 sampling without any fine-tuning, and that is still better. So that's the violet line. But if you combine ILF with best of n sampling, this yields further improvement. So that is this star at the upper right corner of the slide. And that is slightly above 50% win rate, which effectively means that humans prefer those summaries more than human summaries. So it kind of suggests that with this procedure, with ILF, we were able to bring GPT-3 to human-level summarization performance. And that is GPT-3. It was a long time ago. It was a dumb model. And this whole thing suggests an alternative or a complementary to RLHF solution to aligning language models, where you don't have an explicit reward, but you use human feedback to implicitly define this distribution of synthetic data that you can use for fine-tuning. That is actually what I find most interesting conceptually about imitation learning from language feedback, that it is basically just supervised learning. It is basically just fine-tuning on synthetic data. It's just that those are synthetic data generated from the very model you are fine-tuning with some additional optimization pressure, some additional curation. And that seems to help a lot. And you could see this whole process as conditioning, in the sense that the evidence about human preferences that you condition prior on comes from this recursive calls to the language models and humans. So the target distribution can be defined in terms of this probabilistic program that involves sampling from model, asking humans, and then sampling based on the results of that. And that feels like a very flexible and scalable approach, especially today when we are thinking a lot about LLM agents and tool use. You could see just an agentic scaffolding with a bunch of tools as defining some implicit distribution. And then you could use samples from it for fine-tuning. And my claim is that in some deep sense, it is kind of equivalent to RLHF. Yeah, and obviously the human part here is not really that fundamental. There was a lot of follow-up work when the human providing feedback is replaced by another language model, and then you can observe similar results. In some sense, the whole agentic paradigm, like if you think about methods such as React or reflection, when a language model is asked to iteratively work on a problem, to call tools, to reason about results of tool calls, this is kind of giving feedback to yourself. So in my mind, it fits this entire paradigm. But okay, let me move on. So far, I was talking about methods that focus on conditioning a base model during fine-tuning. But you could ask whether we could somehow learn the target distribution directly. And in the last part, I am going to explore basically this idea of pre-training with human preferences. So I started with this problem of fine-tuning a pre-trained language model. The problem of the objective that we use for pre-training language model being in some sense misaligned with human preferences. And the dominant approach is to use RLHF to fix that during fine-tuning. So you pre-train a model, burning a lot of compute, using some slightly flawed objective, and then you burn a bit more of compute to fix the flaws of that objective. You could argue that it might not be the most efficient way. One problem is that we know that language models are quite resistant to forgetting the pre-training data. We have some evidence that larger and larger models and more resilient to catastrophic forgetting, which is typically a good thing, but sometimes tends to be a bad thing, in a sense that it might be really hard and very sample inefficient to get rid of some behavior that was learned during pre-training. And you could then argue that why couldn't we just filter out bad content from pre-training data? We are kind of doing that. It's not that labs are fine-tuning models on just raw common crawl, but there is a bunch of problems with aggressive filtering. First, it handicaps LLM capabilities. It means throwing out good data that you can learn something from, especially in the regime in which we are going to be increasingly data constrained. This feels very uneconomic to just throw out, for example, data with Python code that violates some standards, or with slightly faulty solutions to math problems. You can still learn a lot from that. Another problem is that it reduces the diversity of your data. And again, you have some evidence that properties like robustness to jailbreaks are strongly correlated with the diversity of training data that were used to train a model. So we would like to expose models to diverse distribution of pre-training data. We would like models to know a variety of different situations. And in some sense, we would like them to also know and understand the bad stuff. We would only like them to not imitate the bad stuff at deployment time. And the final thing is that sometimes just filtering out content from pre-training data can amplify human biases, especially if there is some correlation, for example, between some language varieties and some kinds of content. Then you can, for example, filter out African American English varieties because there is some spurious correlation. And that is typically a bad thing to do. And that motivates the question, can the pre-training objective itself be aligned? Can we somehow learn from the entire pre-training distribution by letting the language model know what not to imitate at deployment time? And that motivates the approach we propose in the paper, pre-training with human feedback. And here the idea is simple. We assume that the model has access that, in addition to pre-training data, we also have access to some reward model that can predict human judgments on pre-training documents. And then we would somehow use this additional piece of information during pre-training by showing the model all the documents, just with this additional piece of feedback that would tell the model what not to imitate at inference time. We evaluated 5 objectives for pre-training with human feedback. The simplest one is just filtering out some documents below a given reward threshold. This has the disadvantages that I mentioned a few slides ago. Another one would be maximizing the unlikelihood as opposed to likelihood of such documents. You could also try to augment the training data with control tokens, marking which documents are good and which are bad, meaning that they shouldn't be imitated at deployment time. And you could also just try to rescale the token level language modeling loss by a reward associated with a given document, or you could rescale them by advantage. Advantage meaning reward minus a value function, which is kind of a average reward. We evaluated those models on 3 tasks: avoiding generating offensive content, avoiding leaking personally identifiable information such as addresses and names, and generating Python code compliant with PEP 8, the style guide for Python. We experimented with GPT-2 small-sized models, which were tiny even back then, but we trained them on compute optimal pretraining datasets according to chinchilla scaling clause, which effectively means that it's kind of the optimal location of compute for a given model size, which makes drawing inferences from scaling clause much more justifiable. We evaluated objectives for pretraining with human feedback in terms of 2 metrics. Alignment, which is basically how well unconditional samples from a given model satisfy human preferences, and capabilities, which we operationalize as the Hale divergence from GPT-3, a highly capable model. All PHF objectives reduce the amount of undesirable content by up to an order of magnitude, especially on the toxicity task. The rate of generating toxic content at the beginning of training and at the end of training is almost 2 orders of magnitude apart. Also, misaligned content, misalignment scores decrease consistently with no size of plateau, reaping continued benefits from increasing training data. This is a very nice property. Like, we typically like to see nice scaling like this on log-log plots. It is reminiscent of many scaling laws that we like. So this is a nice property that you can just train the model for longer, doing basically normal pre-training, and the alignment just continues to increase. It seems that conditional training is the method that offers the best trade-off between misalignment score reduction and KL overhead. It achieves similar capabilities to standard pre-training while substantially reducing the amount of undesirable content. And then we have a bunch of follow-up experiments specifically investigating robustness and capabilities. So here we measure. So on this previous slide, I was just showing you basically rewards associated with samples from the model, sampled unconditionally. Here's what happens when you sample from the model, asking it to complete prompts chosen by an adversary. So this is basically robustness to jailbreaks. In this sense, we did something like automated red teaming when we ask another model, an API model, to iteratively generate adversarial prompts that elicit undesirable behavior. For example, for toxicity, it's asking InstructGPT to come up with prompts that make our target model generate a toxic response. And we do that for several rounds. Each time we few-shot prompt the instruct GPT model with the most successful attack prompts from the previous rounds. And what this plot shows is that, misalignment score increases with subsequent rounds of red teaming. This is not surprising, like you just exert more optimization pressure, you do more and more thorough red teaming, so it's easier and easier to find an attacks that elicits undesirable behavior from a model. But it seems that models pre-trained with human feedback are much more robust to this kind of optimization pressure. Especially if you look at the orange line, it seems the success rate of those attacks seems to increase slower and slower. And here, for example, even after 10 rounds of red teaming, a model pre-trained via conditional training still has better misalignment score than a model pre-trained using like normal training. So that's the blue line, and still they are an order of magnitude apart. So the idea here is that it seems that it's not just that models pre-trained with human feedback tend to be more aligned. They also are more robust, as in it's harder and harder to elicit undesirable behavior from them. And that's actually, I think, much more important property if you think about how a model would behave at deployment time. Another thing, we tried to measure capabilities of a model in terms of performance on some downstream tasks. So we did some zero-shot evaluation on benchmarks such as HumanEval and Lambda, and also on some tasks involving fine-tuning, such as glue. The question we wanted to answer here is whether aligning a pre-training objective makes it harder for the language model to learn useful representations. So it's basically a question about the alignment tags. How much of a capabilities decrease you need to have because of using human feedback. And it seems that conditional training, that's the orange bar, roughly matches MLE's performance. MLE, again, is the original standard pre-training. And the fact that they had the blue bars and the orange bars seem to be close together provides some evidence that conditional training doesn't negatively impact the amount of doesn't negatively impact representation learning in those models. It suggests that you can learn representations of undesirable content without learning to imitate such content at all times. So in some like very rough sense, the model understands what toxic language looks like. It just knows that it shouldn't say toxic things. And the final evaluation that we did tried to address the question whether fine-tuning with feedback is on par with pre-training with feedback from scratch. So to do that, we compared pre-training with feedback from supervised fine-tuning with the same human feedback, but only after some amount of pre-training. So for that, we use checkpoints from normal pre-training after 50% and 90% of the data, and we continued to pre-train with feedback. And it seems that pre-training with feedback, the orange line, achieves substantially better toxicity score than fine-tuning with feedback. So the gap between pre-training with feedback and fine-tuning with feedback only widens as more tokens available, and they don't seem to approach the same number. It seems that pre-training with feedback plateaus before it's able to reach the same level of toxicity score. And this trend seems to persist across all three tasks. It just seems that in some sense it's easier to learn good behavior from scratch rather than first learning it during pre-training and then unlearning it during fine-tuning. And you could also argue that involving human feedback earlier on translates into greater robustness to red teaming. Here we see that pre-training with feedback from the start is consistently better than using feedback only on the last 10% of the data. For example, for in the middle plot for personally identifiable information, after 5 rounds of red teaming, you kind of get the same level of toxicity as that of the model that was only fine-tuned with feedback on the first half of the budget. So, to summarize, it seems that the simple approach to learning a conditional target distribution works quite well and has almost no alignment tags. And this is perhaps not surprising. The objective here is basically standard pre-training. We only require the language model to keep track of one additional piece of information, those control tokens that we use. Conditional training also seems to scale well in practice. A similar method was used a year ago in Google's Palm 2 paper. It was back when those details were still public. And you can see that using control tokens on only a fraction of pre-trained data still allowed them to decrease their toxicity scores. So for me, the takeaway is that alignment of a language model seems to be closely tied with the quantity of human feedback it receives during training, and involving human feedback throughout the entire pre-training process results in substantially better alignment than the standard practice of aligning language models only during fine-tuning after they were pre-trained without any human feedback. And that suggests that maybe we should just move beyond imitation learning when pre-training language models and involve human preferences from the very start of training. And skip RLHF. I do not think that is the correct interpretation. I don't think we should replace RLHF. I mostly think about alignment during fine-tuning as complementary to alignment during pre-training and other methods. So the way I like to see it, Yann LeCun has this famous analogy of different kinds of learning as different layers of a cake. And one of my collaborators, Ethan Perez, once proposed a similar analogy for alignment with different alignment approaches being subsequent layers of a big wedding cake. They build on top of each other. And one way of seeing this relationship is just conditioning a language model on subsequent pieces of information about human preferences. So you could argue that pre-training with feedback provides a prior for instruction fine-tuning, and which in turn is a posterior of further prompt engineering and scaffold design, and so on. And those subsequent pieces of evidence are itself based on priors. So we fine-tune our reward models from base models. We use model-generated data for fine-tuning and so on. And this bit is actually quite important, as we can be expected to need more and more model-generated feedback when training more and more capable models. But what I like about this conditioning feature overall is that it treats alignment as a continual process of gathering evidence about human preferences and updating based on it. And to me, this feels very different from unconstrained reward optimization. And just, it also feels much more similar to the actual practice of building models at scale. Thank you. This work wouldn't be possible without my amazing collaborators. And now I am happy to take questions.